Today we're going to measure the insertion performance of ArrayList versus PersistentVector with the help of JMH, the de facto standard for benchmarking JVM applications. Okay, so let's start with the ArrayList. We could create a new ArrayList with element type string, then assign that to a variable named strings. Let's not forget to return it, otherwise we get strange results from JMH. And then let's simply fill it up. Let's say 1,000 elements. Let's call the add method and put the empty string in there. It doesn't really matter which string we pick, since we're only passing a reference to the string anyway. So the size of the string won't have any impact on performance. And let me make the variable final to emphasize that yes, we are allowed to call mutating methods on the object, but we're never going to assign to the variable again. So the variable is always bound to the same ArrayList object. Okay, so what happens when we run the code? What does JMH tell us? So first you see some warm-up iterations to give Hotspot a chance to optimize the code and translate it to native machine code, so it doesn't have to be interpreted. And then you get a nice statistics. The units is milliseconds per operation. This is a German comma, which is equivalent to the American dot. So 0.008 milliseconds is the same as 8 microseconds. So inserting 1,000 elements into an array list takes about 8 microseconds. Okay, so maybe we should pick some more elements to get maybe more meaningful results. Let's see what happens then. Well, here you can see that the warm-up is even more important, right? So more than a factor of 2 difference if you hadn't warmed up. That's why JMH is so much better than manually doing this stuff. Okay, now we have 15 milliseconds. Again, this is a dot for you Americans out there. Okay, so this was rather simple. The next thing we're going to do is work with a persistent vector. But before we can write the code, we have to understand how a persistent vector is represented in memory. So a persistent vector has 2 final references. The first reference is called root, you can't see it yet. And the second reference is called tail, which you can see here. And when we insert the first element into the vector, we have an array of size 1, which holds that element. And when we add another element to the vector, which means we get a new vector back with a new tail, you can see that we have a new array of size 2. Okay, and if we add another element, which means we get another vector back which holds 3 elements, then we have an array of size 3. So for very small vectors, you simply have one encapsulated array of size 0 to 32 in practice. Here I limited myself to 3 elements as a maximum, so the slides don't get incredibly huge. Okay, so what happens when we reach that limit? Let me show you. Now the other reference comes into play. The old tail becomes the new root. The name will become clear in a minute. And then we simply create a new tail. Okay, and for the next 2 elements, we simply create new tails. And now we have an interesting problem. The tail is full, the root is full. We don't allow tails or roots with more than 3 elements. That's what I mean by full. So we have to create a new root that references both the old root and the old tail, which looks like this. And now you can see for the first time the tree-like structure of vectors. So this tree will get bigger and bigger and bigger the more elements we add. Okay, and here's our new tail. Of course, we can add more elements. We will get larger and larger tails. Now the tail has reached its maximum size, so we simply create a new root that also links to the old tail, which looks like this. And then we can add more elements into the tail. Now we reached the maximum. The root is also at its maximum already, so we have to create a new array that links to the tail, and we have to create a new root that links to the old root and that new single element array. That looks like this. Okay, cool. And here's our new tail. Let's make even bigger tails. And now what happens if we add another element? this tail can now be incorporated at this level. We simply create a new array of size 2, and then we have to create a new root that references that new array, which you can see over here. And then the tail grows as usual. So that's the internal representation. Let's see how efficient this is in code. Okay, so first of all, let me remove this comment so we don't forget to benchmark. Then let me blindly copy paste the code down here, and let's correct the types. So persistent vector instead of ArrayList, persistent vector instead of ArrayList. And this is an interesting point. Clojure doesn't allow us to create a new empty vector. And the reasoning behind that is easier to understand if you think as a vector like a string. These types are very similar. For example, here, instead of saying I want the empty string, I also could have said I want a new string that is empty. That is perfectly possible, but every IDE will warn you that this is probably nonsense. New string is redundant, right? We don't have to create a new string. We can simply use the string, the empty string that is already there. Right? It's no problem if multiple parts of your program share the same empty string, since it can't be mutated anyway. Okay, so how do we access the empty vector that already exists? There's a static field for that. Here you can see it. Okay, and now since vectors can't be mutated, we have to get rid of the final, because now instead of mutating the object as we did here, now we have to mutate the variable. Let me show you how we do that. So instead of calling the add method, we call the cons method. The cons method won't change the vector. Instead, it will give us a new vector that is slightly bigger. And then we have to assign that vector to our variable so we don't forget about the new bigger vector. So this is similar to strings. Again, if you have a string and you say I want to concat 1 to 3 to the string, what happens is that this expression gives you a new Java string that has 1 to 3 at the end. But if you don't do anything with it, for example, if you just put a semicolon at the end, then you did some work for nothing, right? The variable still won't have 1 to 3 at the end of the string, so you have to reassign that result. Okay, and for integers, it's even more obvious. If you simply say I plus 1, some languages allow that, the new value will be computed and you simply forget about it. Of course, you have to reassign it, right? And you have to do the same for strings, and you have to do the same for persistent vectors. Otherwise, you do some work for nothing. Okay, let's see how that behaves in the benchmark. That should be interesting. The simple, straightforward, mutable, object-oriented ArrayList and the slightly more complicated structure with a tree inside, completely immutable. This method doesn't change the object. Instead, it gives us a new object and we have to assign that back to our variable. Does that have completely terrible performance, or how does it perform? And here you can see it's not even twice as slow, right? So it's about a factor of 2x. That really surprised me, especially before I understood how that tree structure worked and especially how the tail worked. Right? Without the tail, the vector would probably be much slower. Okay, maybe we should look at the vector again. What are we doing here? So we start with an empty vector, and sometime later we return a populated vector, and it's very important to us that we return an immutable version. But inside the method, there would really be no harm if we had some internal mutation, right? Nobody would be able to tell a difference, and maybe we can get faster. Let me explain to you what I mean by that. If we look at the slides again, we can see that the tail, if we insert elements, is always blue. That means that every time we insert an element, the complete elements in the tail have to be copied over into a slightly bigger array, right? That doesn't sound very performant. So this updating of the root, that happens from time to time, in practice every 32th insert, so about 3% of the insertions. But the modification of the tail happens every time. How about we make the tail, let me begin, we make the tail as big as possible from the get-go. So we don't start with an array of size 1, but we start with an array of size 32 in practice and 3 on the slides. And then we don't have to create a new array. We simply would have sufficient space here for the B and for the C. And we only have to create new tails when the old tail was really completely full. Okay, so we accept some mutability to increase the performance. And I'll show you in the code how that is done exactly. Okay, so the normal vector has an immutable tail, and if you want a variant that has a mutable tail, you simply call the asTransient method, and then the type changes. Let me change the type of the variable. The method is named slightly differently, so probably you don't get confused which variant of the vector you're currently dealing with. And at the end, when we have successfully populated the vector, we want to get back into nice immutable land. Okay, let me start this. Okay, and what I didn't discuss yet is if you compare that to the solution above, we don't have these angle brackets with the string. So Clojure is a dynamic programming language. It doesn't have generics in the implementation of the collections, even though they're written in Java. So you're just going to have to deal with it or look for a library like Waver, which has vectors with generics. Okay, and here you can see an interesting result. So basically, if you squint your eyes, both ArrayList and PersistentVector have the same performance. Okay, so you have no performance disadvantages just by using persistent vectors over ArrayList. And you can see this error will get smaller if you don't have a recording software running in the background, as I have to do for your viewing pleasure. What would also be interesting is to provide the array list with the final size that we already know, right? We know that it is going to be 1 million elements at the end, so the array list doesn't have to resize its internal array all the time. I leave that as a homework to you to see, does it make it 2 times as fast, 3 times as fast, 5 times as fast? You can find it out on your own. And sometimes people wonder, should I use an array list? Should I use a linked list? Why don't you simply copy this array list method, change all the array lists to linked list, and then simply measure the difference? I strongly recommend that you use at least 1 million elements or 10 million elements. Otherwise, the results aren't that interesting. Okay, I hope you found this little animation interesting. I hope it helped you understanding how a persistent vector is represented internally in memory, this tree structure, the tail, how that makes everything efficient. So you're not afraid of using functional programming and immutable data structures, be it in Clojure or be it in Java or any other language. Bye.